All right, so just like um, the last sample problem video, um, this one will also have a lot of problems, and the my purpose here is to give you the general solution process, where I mean I probably do go into more details than I'm originally planning to, but some parts may be skipped over pretty quickly here. So here we have 1, 2, 3, 4, 5, 6, maybe 7? Yeah, 7 total problems this time. Okay, so 7 total problems, so you can jump ahead into the video to find other problems if you'd like. So I'm going to start here by, so these are all going to be sample problems on thermal effects on axial thermal effects. Okay, and so this first one, we just have a block. It's actually a polyethylene block, so it has a pretty low elastic modulus here, and some of its other material properties are not like our typical structural materials, but we're given the material properties and the geometry of the system. We're getting the gap up here is 1/10 of an inch, and it's being subjected to a temperature change of so a temperature increase of 100 degrees Fahrenheit. And I've added a part C here because it's a lot like your homework. But what we want to find is just after that 100-degree temperature change, what's the normal stress, the normal strain, and the change in the width of the block. And that's the part I've added, the change in the width of the block, where there I've just given, I looked up a typical Poisson's ratio for polyethylene, and it's about 0.46. Okay, so first we have to decide whether for this temperature increase if our thermal deformation has been restricted. All right, so that will tell us whether the material has a stress in it or not. So if the material is free to expand with the temperature change, with its thermal deformation, then there's no stress. There's no thermal stress directly. There's only a stress when a thermal strain or a thermal deformation is restricted. And that's going to happen in this case if that gap closes completely as the material expands due to a temperature increase. So what is the deformation, the thermal deformation only, if there's no restriction? So we just take the thermal deformation, it's just the thermal expansion coefficient, multiplied by the temperature change, multiplied by the original length, multiply it out, we find the thermal deformation, if there was no restriction for the 100-degree temperature change, would be about 0.25 inches, which is 2.5 times bigger than the gap. So the gap will be closed at the 100-degree temperature. It's actually going to be closed much earlier than that, and so therefore we will have a stress, a non-zero stress that develops, and we call it thermal stress because it is from the temperature, but it's really from a thermal deformation being restricted. Okay, so our next tool, we're just going to jump to the second tool here, which is force deformation temperature. And that will be able to relate our deformation with the internal force. And now we have the part, our deformation associated with the internal force and the deformation associated with the temperature. Our geometry of deformation is pretty straightforward here. It just says that the total deformation is limited to the gap height, right? The material, the member can't deform any more than the gap. And we determined that it's going to close the gap. So the deformation is just 0.1 inches. All right, and that's what geometry of deformation gives us. So with that, we can then solve, combine 1 and 2 and solve. All right, and that's because everything is known here now. Now that we know what delta 1 is, everything is known except for the internal force. And so we can solve the force deformation temperature relationship for the stress, which is just F over A. All right, so we write it in terms of the stress. It's just going to be stress times length over the elastic modulus plus this thermal deformation part. That needs to equal the 0.01 inches. right? And solve for sigma 1. It's just going to be the deformation over the length minus the thermal expansion coefficient multiplied by the temperature change, the whole quantity multiplied by the elastic modulus. If we plug all that in, we find the stress is about minus 0.561 kilopound per square inch, KSI, which is minus 561 PSI, pounds per square inch. All right, the negative tells us it's in compression, and does that make sense? Well, we had a thermal expansion being restricted, and so in practice, the material is going to feel like it's being compressed, right? It wants to expand more. It's being restricted, so therefore, it's going to have a compressive stress. All right, good. The strain then, well, we just take the total deformation, divide by the length. Well, that's actually pretty easy. Because the deformation is just 0.1 inches, right? The gap closed completely, and it limited the deformation. So it's just 0.1 over 32 inches. We get a strain of 3,125 microstrain, right? And this is actually a result of well, we have a really low stress, but a pretty high strain, and that's what I was saying with the polyethylene having a very low elastic modulus compared to like, steel, which is, it's about 1,000 times bigger of an elastic modulus. So this is not very stiff. So even for a low stress, it has a really high strain. All right, so to get into the last part, which was what's the change in width, we need to think about the lateral strain, right? So the strain, not in the long direction, but in the wide direction, in the width here. We're given that it's a 2-inch block wide, 2 inches by 2 inches. So either direction, we can consider this as either of those two lateral directions that we're looking at. So the lateral strain is going to have two components. First, a lateral strain due to the stress inside the material. Well, that comes from Poisson's effect. All right, so we can relate that to the longitudinal stress through Poisson's effect. And the other component is a lateral strain due to thermal effects. Well, and that's just the thermal expansion. So the material doesn't have the material and how it expands in response to temperature changes, it doesn't care what direction you're looking at. It's going to expand in all directions the same for thermal effects. For internal force and the stress effects, that's not true. If it's being compressed, right, which we have here, we found a compression. It's also at the same time going to expand in the lateral directions. So we have a thermal expansion from an increase in temperature, and we have an expansion due to the compressive axial stress through Poisson's effect. Okay? So this longitudinal strain due to the due to the compressive stress, well, that's just going to be the compressive stress over its elastic modulus, right? So that this is not. Be careful here. This is not the strain we found here, because this is the total strain. Here we're just saying this is just the strain due to stress, which is just the stress over the elastic modulus. Okay? So our lateral strain then, once we plug everything in, we just get a strain of almost 10,000 microstrain. So it's again a really, really large strain to what we're used to. But then we just, to get the actual change in width, we just take the strain multiplied by the original width. Okay, and that's because strain is defined to be the change in something, the change in some length over the original length. So in the lateral direction, that's going to be the change in width over its original width. Solve for the change in width by multiplying through by the original width, and we find that the change in width is just 0.01775 inches. Okay, so therefore the old width was 2 inches. The new width is a little bit longer, 2.01775 inches. All right. So that is a nice first problem. I think now I have 3 problems here. The next 3 are all going to be where we have some sort of a bolt connecting 2 parts, or in some way we're going to be dealing with bolts that have a nut on the other end holding something in here. So we have 3 problems on this, kind of dealing with different aspects of axial thermal effect the problems that deal with thermal effects. All right, so in this case, we say that the nut is hand tightened, so there's no gap at all, but there's also no axial force in the bolt originally. And what I mean by originally is at 40 degrees Celsius, and then the temperature drops by 50 degrees Celsius, which if you don't have an intuition for that, that's actually a huge drop. 50 degrees Celsius is quite large. So we're going to have some non-negligible effects. What we want to know here is basically the internal force, or the clamping force. So as the bolt cools, right, it's going to want to contract, but these are rigid parts, right? So that contraction is going to be restricted, and so it's going to exert some force on the rigid parts, where it's not going to cause any deformation because that's assumed to be rigid. Okay, what is deformable is the bolt itself here. Okay, so for that clamping force, we'll then determine the normal stress and normal strain in the bolt as well. All right, so here's all the properties given to us, including the temperature drop of 50 degrees, and there's what we're finding. Start with the force deformation temperature relationship. Our geometry of deformations, well, the parts are rigid, so our deformation is limited to 0. The bolt can't actually have any deformation since we assume those parts are perfectly rigid. Okay, so the bolt is trying, due to the temperature change, the molecules inside are trying to get closer together, but they just can't because of the restriction, and that's going to produce a stress, right? Okay, so we can combine 2 and 3 here, or just basically set this left-hand side equal to 0, and solve for the internal force, and that is the clamping force. Okay, so everything else is known except F1. Solve for F1 and plug in the values, you get 45.2 kilonewtons, and that's in tension, right? The bolt wants to contract, it can't, so it feels like something is pulling it apart in a tensile fashion. Okay. With that, we just divide by the cross-sectional area to get the normal stress. The normal stress, again, in tension is 119 megapascals. And then the strain, well, the strain is just, total strain is just total deformation over length. Our deformation is 0 because these are rigid parts, so therefore there's no strain. Okay, so this is a case where, we presented and said, well, thermal effects only cause strain, right, and no stress. Well, that's only if the deformation is unrestricted. If it's perfectly restricted, in this case, either it allows no deformation, then we get no strain and everything goes into stress. Okay, so now we'll take that idea and expand on it a little bit. Here we have something very similar, a bolt with a nut, and here it's hand tightened, but when it's hand tightened there, it does leave a gap. The gap is now 0.06 millimeters between the two pieces of, the two rigid parts here. I've drawn this out as wood, wooden boards of some kind here. All right, so what I want to determine here is the temperature at which the gap closes, and then we'll determine the stress and strain inside the bolt when the temperature is 10 degrees Celsius. And I should say, this hand tightening was done in summer, let's say. So in the summer in Bozeman at 30 degrees Celsius, when the temperature was 30 degrees Celsius. So maybe you put something together in your garage in the summer. It was 86 degrees Fahrenheit outside, and you left this little gap between the wood. And then you left it out in your garage through fall, so at 10 degrees Celsius, and then at winter when it dropped to minus 20 degrees Celsius. And I have all the Fahrenheits here as well. So 86 degrees Fahrenheit in the summer, and then it dropped to 50 degrees in the fall and minus 4 degrees in the winter. What are the stress and the strain in the bolt at those times? Okay, so part A, the gap closes when the thermal deformation is equal in proportion to this gap, but in a negative fashion. So we need to have a negative deformation of the bolt because we want it to shorten by this gap. All right? So that's when the gap closes. The thermal deformation is its expression is here. The only unknown here is the change in temperature. We can solve for the change in temperature and find it's a minus 40 degrees Celsius temperature change. And so that means the temperature at which the gap closes, take our original temperature, 30 degrees, add on to it the temperature change, which is a minus 40 degrees Celsius change. So at minus 10 degrees Celsius, the gap will close. Okay, so now you can see why I chose these two temperatures. In fall, the gap hasn't closed yet, and in winter, the gap has closed. So we have two different, qualitatively different systems here. So at a temperature of 10 degrees Celsius, the gap has not closed yet, so we'll have no stress. The thermal strain, well, that's just going to be the total strain is just going to be purely thermal strain. Thermal strain is just the thermal expansion coefficient multiplied by the temperature change. Our temperature change here is just going to be, well, we started at 30 degrees Celsius, we're now at 10 degrees Celsius, so there was a minus 20 degree temperature change in Celsius. So the thermal strain is just going to be minus 300 microstrain, and that is the total strain because there's no restriction to deformation yet. Okay? But when we get into winter, when the temperature drops even further, the gap now closes because the gap closed at minus 10 degrees Celsius. So now the gap is closed and we get a non-zero stress. Okay? And that's because the deformation is restricted once the deformation reached that 0.06 millimeter gap. All right, but our strain is now going to be quite easy to calculate because now our deformation is restricted at the gap distance, and divide by our original length, we find a strain of minus 600 microstrain. But our stress is now non-zero and requires a bit of care here. So we take our forced deformation temperature relationship. We now know that the deformation is minus 0.06 millimeters. And hidden inside there is the stress that we're looking for, F over A. So we solve for the stress because everything else is known. Plug in values. I did relate it to strain here, but we just plug in the values when we find that the stress is 30 megapascals in tension. So this is again the same thing we had before. The bolt wants to contract beyond the gap distance, 0.06 millimeters, but the contraction is restricted because the gap is now closed and the boards are rigid. So that causes tension. That feels, the bolt wants to contract, it can't, so it feels like it's in tension. I use these words that give it human traits or human thoughts, but maybe that's a little bit something I should avoid. Okay, so this next problem still deals with the bolt, but now we have a sleeve on the outside, and this one now comes straight out of the book again. You can read the problem description here, but essentially we have a bolt into the wall of a machine with a sleeve on the outside, and there's a washer here too, so the bolt is an extra 5 millimeters longer than the sleeve. But regardless, here are all the givens in this problem statement, and we want to find the stress and strain inside the sleeve on the outside. The sleeve is composed of, where is it, bronze, and the bolt is composed of steel. And I just read that out of the problem statement. Okay, so now we're going to start with, and now let me make a note. With this, now that we have two different materials and two members that are deformable here, this is going to be a statically indeterminate system that has a coaxial geometry with a temperature change, delta T. Okay, so we're getting a little bit more complicated in the types of analysis needed because we're combining here statically indeterminate systems with temperature changes. Okay, and the only difference here from what we did last time here is that the second step now is not the forced deformation relationship, it's the forced temperature deformation relationship. So the first step still involves equilibrium, drawing a free body diagram that exposes the internal forces, getting a relationship between the forces from equilibrium, and there's no applied load here, so it's actually it's a really nice relationship, and that is that we can perfectly relate them. But regardless, it's indeterminate because we can't determine them completely. We can just have a nice expression between them. Our second tool is forced deformation temperature. So we've just drawn out those two relationships for each of the two members. Our geometry of deformations, this is coaxial. So delta 1 must equal delta 2. There's no gap here, so the deformations go together, right? As one contracts, two will contract. And Is the temperature increasing? The temperature is actually increasing. So as 1 expands, 2 will expand in equal proportion. Okay, we can then combine 2 and 3, our force deformation temperature relationship, with the geometry of deformations to get the compatibility equation. And that doesn't look so bad. We just basically put an equal sign there. And then we can plug this, and now this is our second relationship between F1 and F2. So we can plug in the result from equilibrium into our compatibility equation, and then we'll just have one equation for one unknown. So F2 here. Okay, so what I've done here is taken F1, replaced it with minus F2, pulled all the F2s to one side, and then pulled everything else to the other side. We can then solve for the stress into F2 over A2. All right, so that's going to be the stress in 2. And that's given by this formula here, so you can work through the algebra. The areas here, we have to be a bit careful here. The area for the bolt is just pi over 4 times its diameter squared. That one's pretty easy. But the area for the sleeve was given as an outer diameter and a wall thickness. So we've done this before, but be careful there. Oh, and that wasn't on the page. In fact, I've probably been off the page for a while now. So let me just run through it again really quick, but we just plugged the result from equilibrium, the simple result from equilibrium, into the kind of more complicated compatibility equation, got an expression for just F2 and solved for F2 over A2 to get what the normal stress in 2 is. Okay, here's where I was talking about the areas. The area for the bolt is the standard pi over 4d squared, but the area for the sleeve is going to be this expression where we were given the outer diameter and the wall thickness. So the inner diameter is just the outer diameter minus 2 of the wall thicknesses. All right, so at that we can then plug everything in. We get this complicated expression here. The normal stress in 2 is just minus 27.1 megapascals, so it's in compression. Does that make sense? Compression. Temperature increased. Temperature increased in 2. Well, actually, so I don't, we might not be able to have a intuition about this, but basically what we're saying here is that, the bolt and the sleeve, you can see here from equilibrium, one's going to have a positive internal force, the other one's going to have a negative internal force. So therefore, one's going to be in tension, one's going to be in compression. What we're saying there is one's going to want to expand quicker than the other one, but they're limited in their deformations go together, right, from the geometry of deformations. So that's going to result in one being in tension and one being in compression. And in this case, the sleeve is in compression. Okay, and the second part is what's the strain in the sleeve, and that's just going to be the deformation of the sleeve over its length, where the deformation of the sleeve is given by its force deformation temperature relationship. Okay, we can simplify this a great deal. We have F2 over A2 is just sigma 2, and we just calculated what the normal stress was. The L2 cancels, so this first term is just the normal stress over E2. And the second term, well, it has an L2, and then we're dividing through by L2, so that just becomes the thermal expansion coefficient multiplied by the temperature change. And then when we do the, calculate the strain, we find a microstrain of, or a strain of 1,326 microstrain. Okay, so that completes our set of 3 problems dealing with bolts. And you can see we got a little bit more complicated there at the end because we started considering statically indeterminate axial members with temperature changes. And that's what this one is also, but here the geometry is now end-to-end, as in the last one it was coaxial. So here we have an end-to-end statically indeterminate axial member. Let's see here, we're given, and now in this case, the other complication here is that we're given the yield strengths of the deformable members 1 and 2 and factors of safety. All right, so what here we're not given what the temperature is, what the maximum decrease in temperature is. sorry, we're not given what the temperature change is. Instead, we have to determine what the maximum allowable decrease in temperature is, such that the yielding the normal stress in our deformable members is limited based on their constraints due to yielding. Okay. So this one is going to have this, considering two different design constraints aspect of it. But here we have, we're going to start with the equilibrium, draw a free body diagram that exposes the internal forces. Right, so we just have a free body diagram of BCD. And we get, again, a nice relationship between the internal forces. And that's because there's no applied loading here. We're just going to have a temperature change, and it results in a really nice relationship between them, something that looks easy. But this is going to get more complicated as we go along because of we're not actually given what that temperature change is. So our next tool is the force deformation temperature relationship for each of our members, delta 1 and delta 2. We can then combine the deformations through a geometry of deformations. This is end-to-end. So as you know, if delta 1 compresses, if delta 1 contracts and shortens, delta 2 must then elongate in equal amount as BCD shifts, right? So we write that out by saying the sum of the two deformations must be 0. Combining 2 and 3, we get the compatibility equation. Okay, so at this point we have two equations for F1 and F2, and it doesn't look too bad, but we should also say here, it looks like it's two equations for two unknowns, but we don't know delta T either, right? That's not given in the problem. If it was, we would just march ahead and do what we did, solve for one of the forces here, plug this result down here and solve for one of the forces. All right, so we have to do things a little bit differently here, because 1 and 2, those two equations are really two equations for three unknowns where delta T is unknown. So we can use the result from equilibrium and the allowable stresses to then determine F1 and F2 completely. Okay, so we actually don't need to get back to the compatibility equation until we've already determined F1 and F2. Okay, and that comes from the allowable stresses. All right, and so let's see how that works here. Here we have the allowable stress in 1 is given by its yield strength divided by its factor of safety. All right, and that turns out to be 172 megapascals. And the allowable stress in 2 is its yield strength over its factor of safety, so 110 megapascals. All right. So those are the allowable normal stresses. We can then associate with those allowable internal forces. So the allowable internal force in 1 is just going to be its allowable stress times its area, found here. And the allowable force in 2 is just going to be its allowable stress times its area, so its allowable load, the allowable internal force is out here. All right, so now we have two allowable forces, and from equilibrium we have a relationship between the forces. So with that we can just determine which internal force controls the systems. So if we take F2 to equal to its allowable force, it's like 54 kilonewtons, right? At that, we plug this into the result from equilibrium. We get that F1 equilibrium says F1 equals 2F2. So in that case, we get an internal force of 108 kilonewtons, which is bigger than the allowable force in 1. Okay? So this means that F2 doesn't control. We can't allow F2 to be at its allowable we can't allow F2 to be at its allowable. Instead, we're going to F1 controls, and F1 is going to be at its allowable limit. All right. So F1, we set that equal to its allowable load. Calculate what F2 is from our equilibrium result. We get, well, now this is fine, right? So this is the associated internal force in 2, and it's much lower. It's less than half even than its allowable load. Okay, so this means that F1 controls the system, and here are our internal forces. We just calculated them. So at this point, then we do take our compatibility equation 2 and solve for delta T, where now we know what F1 and F2 are. So here I've just solved for delta T from our compatibility equation. Plugging everything in, we find that the maximum it's really the maximum decrease in temperature that's allowed is 50.15 degrees Celsius. Okay. Now we have two rotational systems. So all that's left here are statically indeterminate axial members that have a rotational geometry to them. Okay, so in this one we have a rigid bracket ABC. It's and this is kind of so I wrote this problem because it's we got to throw it up in outer space here. So let's say this rigid bracket is being designed for the International Space Station. It needs to be connected in this geometry for some reason. It has rods 1 and 2 that are unstressed and unstrained at the original temperature of 20 degrees Celsius. All right, we're given that they have the same cross-sectional areas and the same lengths, 1 and 2, but 1 is a steel rod and 2 is an aluminum rod. And it's such that the steel rod has 3 times the elastic modulus than the aluminum rod, but half the thermal expansion coefficient. Okay, so E1 equals 3E2, and then alpha 2 equals 2 alpha 1. All right, and if you look up these properties in the back, that's actually pretty close what they are, but what I'm doing here is that we're going to get a lot of ratios between these two things, and it'll make our ratios a lot easier. What we want to determine is the stresses inside 1 and 2, the stress, normal stresses in 1 and 2, at 2 different temperatures that are extreme temperature differences. So 120 degrees Celsius on the sun-facing side of, the outside of the International Space Station, and when we go to the dark side, so on the dark side of the Earth, the temperature can drop on the outside of the International Space Station to minus 160 degrees Celsius. So these are extreme temperature swings. Okay, so start with equilibrium. We draw a free body diagram that exposes the internal forces. It also exposes the reaction forces at B. So to isolate, we can see here we have 4 forces and we only have 3 equilibrium equations, so we already know it's going to be indeterminate. But we really only need the moment about B equation because that'll just relate F1 and F2. And we only are interested in F1 and F2 because we want the normal stresses in 1 and 2. So the moment equation, summing the moments about B and setting it equal to 0, we find that a relationship here between F1 and F2. Our second tool is the force deformation temperature relationship, and a relationship for each, for 1 and 2. And then the third tool is the geometry of deformations. All right, so this is where it gets a bit trickier, and we have to be more careful. Let's assume a clockwise rotation. All right, so we don't really know what a temperature change is going to do right away, right? We don't know if the temperature will cause, it really comes down to whether member 2 or member 1 wants to compress or expand more. I mean, you can actually look over here and see the thermal expansion coefficient is bigger for the aluminum rod. So the aluminum rod will respond more to temperature changes. And because everything else is the same, the area and the length, that should tell us a lot about the system. However, it gets a little bit contorted here when we have different elastic moduli as well. So it's hard to have a prediction about this. So we'll just assume some sort of rotation, and it actually won't affect the system because all we're going to do here is relating the relative deflections at A and C. So if they're either we were right and these are both positive, or we were wrong and they were both negative, but it really won't matter because all we're interested in is their relationship. Okay, so we assume a clockwise rotation to draw a nice picture, and then we just have similar triangles again. For the way I've drawn it, this means that member 1 is in tension, and member 1 elongated, I guess, let's say. I don't want to use the words tension and compression. We just want to say member 1 elongated, and member 2 here is shortening associated with this clockwise rotation. So the similar triangles, the distances from point B are given in terms of just A here. So this is basically just says that A is twice as far away as C is. So our similar triangles, the result here is that VA equals 2VC, but VA is just delta 1 and VC is just minus delta 2, just from the geometry and the and how we relate the deflections of the points to their deformations. And so from all of this, we can combine it to say that the deformation in 1 is equal to minus 2 times the deformation in 2. All right? So here's the result from geometry of deformations. We can combine that with our force deformation temperature relationships to produce our compatibility equation. And now we have two equations here. Here's our first equation that relates our forces, and now here's our second equation that relates our forces. All right? So now we're at the point where we can solve this, and we could now consider the two different temperatures of interest, but I'm actually going to go forward here keeping it completely general, and that way when we get to the final result, we can just plug in the two temperatures for just the final equations. All right, so what we're going to do here is plug the nice relationship 2F1 equals F2 from equilibrium into the more complicated compatibility equation and solve for F1 over A1, which is our normal stress in 1. So we plug that in. Now we have just one equation for F1. You see F1 here and F1 there. And so we pull all the F1s to the one side, and we have this term on multiplied by it, and it equals everything else over here that doesn't have an F1 in it. And now we start looking here. I say, remember from our givens, A2 equals A1, L2 equals L1, E2 equals 1/3 of E1, and alpha 2 equals 2 times alpha 1. All right, so that's going to simplify things a great deal. Basically what I want to do here is write everything, replace all the two subscripts with one subscripts, and then if they need to be multiplied by the proper factor, we'll put those in there. All right, so you can see, let's say, so L2 was just L1, so we could just replace L2 with L1 and pull it out front. E2 is 1/3 of E1, so that's why we see a 3 over E1. That came from 1/3 E1. The areas are the same, so we just pull out A1. Okay, so that explains all that. And we did the same thing over here with alpha 2. Alpha 2 was just 2 alpha 1, and so that's why we see 2 alpha 1 there. All right, with that, well, these are both 1 over E1, and we have 12 there and 1 there. This becomes 13. And then this is 4 times alpha 1 plus another alpha 1, so we get a 5 here. Okay? And with this, we can then, now it's pretty easy to just solve for normal stress in 1. It's just F1 over A1. So we're just solving this for F1 over A1. So we get minus 5/13 times the thermal expansion coefficient multiplied by the temperature change multiplied by the elastic modulus. Once we have sigma 1, sigma 2, well, that's just F2 over A2, but A2 equals A1, and F2 equals 2F1 from equilibrium. So the normal stress in 2 is just 2 times the normal stress in 1. So we get that the normal stress in 2 is just, it's the same exact thing, except instead of 5/13 we have 10/13. All right, so now we have expressions for normal stress, and we're ready to plug in our two temperatures. And they're kind of short expressions, right? A lot of work to get here, but they're relatively short expressions. So on the sun-facing side, let's say, the answers come quick, but then I have a little bit of a discussion about it here. Our temperature change, we went from 20 degrees Celsius to 120 degrees Celsius, so it's a 100 degrees Celsius change. Plug all that in, we find a normal stress in 1 of minus 92.9 megapascals, and a normal stress in 2 of twice that much, so 185.8 megapascals. And they're both in compression. And that seems strange, right? How can they both be in compression when it obviously has to rotate, right? You would think one would be in tension, one would be in compression based on the way it's rotating. Well, not when thermal effects are involved. And that's why it gets more complicated with thermal effects. And when we have temperature changes, what we see in this case with this huge temperature increase, both members want to thermally expand. And in both cases, it's restricted because the other member is there also wanting to expand, right? So with the huge temperature increase, they're both wanting to expand, but they can't. And so that means that they both, the compressive stresses are produced in both members. All right? The other thing is it a clockwise rotation? Well, we can just calculate what the deflection at A is, and because it's just the deflection, just the deformation in 1, the deformation in 1 is given by its force temperature deformation relationship. we can just basically plug all the values in, and we find that in this case the deflection at A is a positive quantity, right? We have a little L, the length of L1, the length of 1 is unknown and never given to us, but it doesn't matter. It's just all I'm doing here is the deflection at A is a positive quantity. So because it's a positive quantity, it means that our original assumption was correct, and then it does rotate in a clockwise fashion here. So A deflects in a clockwise fashion to the right as 1 elongates. If we then go to the dark side, when things get really cold, we now go to minus 120 degrees Celsius on the dark side. So the temperature change is minus 180 degrees Celsius. Plugging this in, we get a stress in 1 of 167.2 megapascals and a stress in 2 of 334 megapascals. And now both are in tension. And for the same reason, this is because they both want to contract. They can't both contract, and so they both develop tensile stresses as their contraction is restricted. And if we ask the same question, is the clockwise rotation valid here? Well, now, if you do the same process, we get a negative result for the deflection, meaning that our original diagram was incorrect, and we actually get a counterclockwise rotation in this case, right? So clockwise, a rotation in the other direction there. And so in this case, 1 is going to shorten as 2 elongates. Okay, so that's that problem. And we just have one more problem, and it's going to be pretty similar to the last one, except it's no International Space Station involved here, no dark side involved here. But it's another rotational statically indeterminate axial member with a temperature change, and we're again just finding normal stresses. Here we're just kind of given one temperature change. And actually, here's something a little bit unique here. Here what we're given is that the temperature doesn't change over here, but the temperature is changing for this member. So maybe this is inside and outside of a building. And so inside the building it stays at room temperature, but outside the building we can get extreme temperature drops. All right, so, member 1 over here is is bronze, and the aluminum one is, member 2 is aluminum, and the aluminum rod is the one subjected to a temperature drop. Okay, so again, we'll start with our first tool, applying equilibrium, exposing the internal forces. It also, the free body diagram exposes the reactions at B, but when we sum the moments about B, we're just going to isolate the 2. And in this case, we have to write out their moment arms, or multiply the moment arms by the forces. And the end result is that F1 is equal to minus 1.75 times F2. Okay, so in this case, 1 will be in tension, 1 will be in compression. Our second tool is force deformation temperature. And we write them out completely, but I have crossed out here the temperature change in 1 because it's just 0. So for member 1, we just have the force deformation relationship. For member 2, we have the force deformation temperature relationship. Our third tool here is the geometry of deformations. Like the last problem, we kind of had to assume a direction. Here we can actually we can make an educated guess and an accurate, we can actually know which way it's going to rotate here. So member 2 has so member 1 has no temperature change, but member 2 has a temperature drop. So member 2 will want to contract, right? And that will be restricted by member 1. So we're going to get stresses in both because of the restriction from 1. But we know that it's going to rotate in a clockwise fashion. Okay, so since the temperature drops from member 2, it'll try to contract partially restricted by 1. So first of all, we expect that member 2 will be in tension because it'll have a restriction on what it wants to contract, right? So a thermal contraction will be restricted, therefore that'll be in tension. And at the same time, member 1 will be in compression as it's restricting that rotation, right? We also can tell from this statement here that ABC will rotate in a clockwise fashion. All right, so we draw out the ABC bar here and apply similar triangles. So that's what we have here. And we relate these deflections to the deformations in 1 and 2. So the deflection at A is equal to the deformation in 1, but with a negative sign there, because this is a positive deflection, but it's associated with a negative, negative deformation. And the same thing over here at C. At C, that's the deflection at C associated with the negative deformation inside of 2. So with that, since they're both going to be negative here, we can just directly replace our similar triangles with the actual deformations in the 2 deformable rods. All right, so there is our geometry of deformations result. We can combine this with our force deformation temperature relationships to get our compatibility equation. So you can see here's that force deformation relationship for 1 with no temperature change, and then the 1 over 200 from the geometry. And then there's the force deformation temperature relationship for member 2 with its 1 over 350 from the geometry of deformations. All right, so then we plug the nice result from equilibrium, this guy, into our compatibility equation, which is quite complicated, but what it allows us to do is to solve completely just for F2. All right, so this is now an equation where the only unknown is F2. All right. So with that, we require a little bit of algebra to solve for, did I have that hidden or was it on there? I don't know. But you can see it now. This is now just an equation for F2. Do a little bit of algebra, we can solve for F2. And I'll just make one note here that this 1.75 came from a factor during our equilibrium stage of 350 over 200. And you can see here we have another 350 over 200. If we were to multiply this to the other side, that would be another 1.75. All right, so this becomes 1.75 squared down here. And, well, regardless, at this point, you could just at any point plug everything in. You could plug everything into here. You could have plugged everything into here and just solve for what F2 is, right? But in the end, you got to find a way to solve for F2. Turns out to be 8.58 kilonewtons, and then you can go back to equilibrium to determine F1, which is about minus 15 kilonewtons. Once we have our internal forces, we can determine normal stresses by dividing by the cross-sectional area, which is probably the easiest part of this problem. And here we have the normal stress in 1 is minus 33.2 megapascals in compression. That matches our hypothesis from before, that member 1 would be in compression, and we find member 2 in tension, which also matches our hypothesis that I discussed earlier. All right, so those are a bunch of problems dealing with axial effects on systems, whether they're statically indeterminate or not, and I tried to have the different types of statically indeterminate geometries, coaxial, end-to-end, and rotational.